Hi everyone. If you're following along, this goes along with homework 10.6, Diffraction and Interference Conceptual. So the point of last night's homework was to figure out when do rays constructively versus destructively interfere, how does this occur with diffraction, and to use this to do some calculations. Today's new part of the lesson will have to do with the calculation parts. But just to recap, in yesterday's lesson, we were dealing with interference. That's when either two waves that are in phase, their amplitudes are going in the same direction, add up to make a larger amplitude, or when two waves are out of phase, you get destructive interference. The crest lines up with the trough of this wave so that no amplitude occurs. To tell the difference between that and diffraction, diffraction is when light, or actually any wave, goes through a boundary or a small opening. So in this case, a water wave, when seen from above, goes through this opening and spreads out. You've heard this before, when a loud class is in the hallway and we're all being quiet in here. That loud class's sound wave travels through the openings of the doors and spreads to fill the whole room, unfortunately. Now, notice that this occurs when the size of the wave, in this case, look at the wavelength here. The wavelength is small compared to the size of the opening. That bending and spreading effect doesn't occur all that much. It works best when you have a wave that's approximately the same size as this distance. Now, why that's important to bring up is you've heard this with sound. But why doesn't light seem to bend around openings or fill a whole room? Well, it turns out that's because usually, in order to see diffraction of light, you need to have really, really tiny openings, ones that are about the same size as the wavelength of light, or a little bit bigger than the size of a human hair. If you have waves that are too small in compared to the opening, like when light goes through normal-sized openings, light doesn't bend around the corners significantly because light is just too small compared to the size of the opening. So that brought us to the double slit experiment. In the double slit experiment, you had two tiny openings right there, separated a distance d. And in some places, the waves add together, the wave from one source and another, to have an antinode in the center. And since we see large amplitude as brightness for light, heat, if we were talking about like the hot spots in a microwave, or loudness for sound, the double slit experiment could actually be done with any type of wave. In a microwave, this would lead to hot spots that would be hot, cold, hot, cold, hot. Or if I have two speakers set up some distance apart from each other, you would hear loud, quiet, loud, quiet, loud. So last night's homework 10.6 then had you start in Fe. And basically, once you get to the wave interference tab, you'd go over to the slits part of the experiment. You would want to change it from 1 to 2 slits. Right? But then you can change it around. So you could do this as water waves. You could do this as sound waves, where these bright spots are representing the compressions and the darks would be rarefactions, but we're going to keep it with light, and we're going to keep it on 2 slits. So for this, it wants you to draw, where did my 2 slits go? Oh, there they are. It wants you to draw the nodal and antinodal lines. So let's put it on a fun color. I'm a huge fan of teal. Okay, I would see a bright spot here, then a dark, then a bright. In this case, I would see my antinodal line goes straight across, would be where my waves intersect, and my nodal lines would just be in between there. So if you're wondering how to draw this, wherever I see crests interact with crest. That's going to be where constructive interference occurs. So this would be my bright spot. Crests interact with crest, so this would be a bright spot. This would be a bright spot. And then eyeball your antinodal or your nodal lines halfway through. So again, bright spots are going to be antinodes, dark spots, nodes. So for part 2, I wanted us to look at the wave interference simulation. So let's get back to PhET and we'll show you what to do. So for part 2A, we're changing the color from long wavelength, like red, then measuring the distance between the antinodes, to short wavelength, like blue. So there's my red, and I see that for red, the distance from one antinode to the other could be measured like this, from one bright spot to one bright spot. Now, red is a long wavelength. In fact, if you want to pause it and measure the wavelength, you can definitely do that. You can pause and measure the wavelength by going from crest to crest. All right, so there's my red wavelength. So, in this case, I want to point out, when I have something like a red wave, it makes bright spots that are really far apart from each other. But if I do the same with purple, because the wavelength is smaller, it makes more bright spots that are closer together. So, takeaway from this part is when I have a long wavelength like red, that makes the bright spots farther apart. And a short wave like green makes the bright spots closer together. Now, if we were in class, which I wish we were, one of the coolest demos of light is to wear these special goggles that use diffraction to make cool shapes. Now, what we'd have to do for that is shine 3 lasers, a violet, a green, and a red, and then put on the goggles. Instead of having just regular openings that are shaped like, I don't know, holes, right? These goggles are special in that they have openings that are shaped like little tiny elves. Or in this case, mine were actually snowmen. I do have a case of like 35 of these, so options, right? So a thing to point out is that the red snowman is larger than green, is larger than violet, because in this case, red has a larger wavelength. And so think of it as like the red wavelength spread out more. If you use special diffraction grading glasses, like the type in this picture, you see that red always occurs on the outside and blue on the inside. And that's because red diffracts with larger interference patterns. Now, I actually think the O-physics simulation does a little bit of a better job of explaining this, showing that with blue waves, the short wavelength means they meet up faster, or meet up more often, we'll go with. Whereas red, as we drag this out, as the waves get bigger, that diffraction pattern gets larger just because the waves are themselves larger. So that red has a large spacing between the bright spots, and blue has a small spacing between the bright spots. Hey, if we want to stay in O-physics for a second, the slit distance D is just how far apart these two little holes are. And we can just eyeball this real quickly. If it's a large slit distance D, then they're really close together. But the smaller I get, think like I want D to be close in size to the wavelength of the wave, the more this spreads out. So this is actually an inverse relationship. The smaller D is, the larger the spacing. In fact, the spacing for Y here, the spacing is so big it's like all the way off the page. And so if we were in class, we would do all these different laser demos where we have lasers going through openings of different, this should be D instead of W, but it's slit separation, distance between the little tiny holes that are in the two pieces of paper, right? As D gets smaller, that spacing gets wider. Right? So 2C then, how does the distance affect the separation between the maxima? Actually, this is basically why I have you in PhET instead of just sticking in O physics the whole time. In PhET, it doesn't let you change the distance L. But to help explain it, think of this projector lens to the screen as your distance L. Can you imagine if I took that screen and moved it across the room? I would see a dimmer but huge flower. If I took the same screen and brought it really close to the lens, if you guys have ever put your hand in front of the lens of a projector, which, if we ever go back to school, I will show you what it does. All right, if you ever put your hand in front of the projector lens, you would see that this would make a much smaller image, still upright, etc. Much smaller image, much brighter. So, the only reason I have you in PhET then is because you can see then that if you have this diffraction grating really close to the screen, that you get bright lines that are pretty close together. And if I bring this far, you get dimmer lines that are farther apart. Right? Part 3 of your lab then should have been super duper easy. For this, I was looking to change wavelength, measure Y, change D, the distance between the two slits, measure Y, graph, come up with relationships, and substitute into our equation. We figured out at the first page that if L goes up, Y goes up. So we know that's going to be direct, that'll be on the top. And the rest of our relationships that we took from the O physics data show a direct relationship for wavelength and distance, right? And an inverse relationship between slit spacing and Y. Those were the two relationships we were talking about with slit distance. If it's larger, it's closer together. And wavelength, changing the color, changes the distance. So review the homework, make any changes you need to change, and then we'll take a look at the new learning for today.